The implications of quantum mechanics has radically shifted the way we view reality. Yet many materialists and dualists cannot handle what quantum mechanics tells us about reality. Bohmian mechanics, or pilot wave theory, is an interpretation that attempts to rescue realism in classical physics from the implications about our reality that quantum mechanics gives us. What it does is it tries to explain the effects and equations of quantum mechanics in the boundaries of a classical theory of physics. Whereas quantum mechanics doesn't follow classical physics and says physical reality is in an indefinite state, a wave function, until an observer makes a measurement. Bohmian mechanics says reality is as it is without observers. Particles are not in multiple states at once in a superposition. In Bohmian mechanics, particles have one speed and one position regardless of whether an observer makes a measurement. So that would imply it is fully deterministic, much like how Newtonian physics is deterministic and not probabilistic like in quantum mechanics. So you can't talk about a path the particle took within an experiment, whereas in the standard interpretation of quantum mechanics, a particle takes all possible paths prior to measurement. Now in experiments, it does appear that there is randomness, which is why quantum mechanics appears to be the simplest interpretation. What Bohmian mechanics posits is the wave function is not a mathematical probability of where the particle could end up, but instead says it is an extra force that guides the particle along its path. It is a guiding wave, or pilot wave. So in Bohmian mechanics, you have to posit an entirely extra force in order to save classical physics. This extra force is what makes the particle appear to be random, but in reality, we simply do not understand the mechanics of this extra force or know each particle's starting position. So we assume randomness, even though this extra force would be at work causing particles to move along their projected paths. Recently, Bohmian mechanics received some media attention from an experiment with water droplets that some touted as evidence for Bohmian mechanics over standard quantum mechanics. But the popularizers did not actually read the papers on the experiments. To quote, "Recently experiments have been made with water droplets surfing on the waves produced by the Faraday instability on the surface of an oscillating tank filled with a fluid. The motion of these droplets mimics the suggestion of de Broglie and of Bohm that elementary particles are likewise piloted by the wave function of wave mechanics. In particular, it is claimed that when the waves propagate through two slits, or are confined in a corral, the droplets satisfy statistics that are similar to those observed for particles in quantum mechanics. But such experiments only demonstrate the universality of wave propagation and the associated path lines when governed by the equations of fluid mechanics, quantum mechanics, or of other sources of waves in physics." Basically, the experiment only demonstrated Bohmian mechanics was consistent with the results, but so is the orthodox or standard interpretation, as is the many worlds interpretation and many others. This experiment in no way gives a leg up to Bohmian mechanics over other interpretations. Now, despite a few proponents, the overwhelming majority of physicists have rejected Bohmian mechanics, and for good reasons. It overcomplicates everything, which the standard interpretation of quantum mechanics doesn't do. One of the most important issues is its problems with special relativity. Although currently we do not have a quantum theory of gravity, and currently are unable to rectify quantum mechanics with general relativity, Paul Dirac was able to rectify quantum mechanics with special relativity. Special relativity simply explains constant velocity of motion through space-time, whereas general relativity takes this idea and applies it to the rest of the universe, and it is a more complicated theory. However, Bohmian mechanics cannot even be rectified with special relativity, meaning it makes less sense with what we already know about the universe. As physicist Lubos' model says, "There's no way out here. If you attempt to emulate a quantum field theory in this Bohmian way, you introduce lots of ludicrous gears and wheels, much like in the case of the luminiferous ether. They are gears and wheels that don't exist according to pretty much direct observations, and they must be finely adjusted to reproduce what quantum mechanics predicts, sometimes without any adjustments whatsoever. Every new Bohmian gear or wheel you encounter generally breaks the Lorentz symmetry and makes the wrong predictions of a Lorentz violation, and you will need to fine-tune infinitely many properties of these gears and wheels to restore the Lorentz invariance and other desirable properties of a physical theory. Even a simple and fundamental thing, such as the linearity of Schrödinger's equation, is really totally unexplained in Bohmian mechanics and requires infinitely many adjustments to hold, while it may be derived from logical consistency in quantum mechanics. Furthermore, physicist Carlo Rovelli notes quantum mechanics does not have any incompatibility with at least the symmetry principles of general relativity. Yet Bohmian mechanics does, mainly because it requires absolute time outside of relativity. What this means is, according to relativity, there is no sense of absolute time for the entire universe. Space and time will be different for you depending on where you are in the universe and how fast you are moving. The old idea of absolute time says that time exists independently of any perceiver, progresses at a constant pace throughout the whole universe, and is the same for every point in the universe, regardless of where you are and how fast you are moving. Einstein, of course, did away with this because it was unnecessary for relativity and did not fit with the data. But to hold to Bohmian mechanics, you have to bring back in this idea of absolute time and reject special relativity to hold to a form of Lorentzian relativity. Now, because physicists were able to combine quantum mechanics with special relativity, we came up with quantum field theory, which is a theory that explains more than just the Schrödinger equation of quantum mechanics. So going on that, as we explained before, Bohmian mechanics is simply an attempt to reinterpret just the Schrödinger equation by interpreting the wave function as an additional force of nature. But quantum mechanics is not just the Schrödinger equation. It includes all of quantum field theory. So even if proponents of Bohmian mechanics would succeed in showing that it is the most simplistic and least ad hoc way to explain the Schrödinger equation, they would only explain that and not overtake all of quantum field theory. There are several issues they simply cannot account for in quantum mechanics outside the Schrödinger equation. So Bohmian mechanics really only applies to non-relativistic quantum mechanics, making it a theory that explains far less by positing far more that is needed. There are proposed solutions to create a Bohmian field theory, but even articles written in support of Bohmian mechanics admit this is still an enigma that Bohmian mechanics has to face. There just isn't a solid mathematical way to accomplish what standard quantum field theory has been so successful and simplistic with. Philosophically, this is made pretty clear. Special relativity follows from two premises. One, that the laws of physics are the same in all frames, and two, that the speed of light is the same in all reference frames. Pretty simplistic and accounts for all of the data in this field. However, to reconcile Bohmian mechanics with relativity, adherents have to hold to the Lorentzian ether theorem, which overcomplicates relativity by adding more unfalsifiable premises. 3, that there exists an extra reference frame, and 4, there is an ether which interferes with clocks and contracts measuring rods with respect to that absolute frame, so as to give the appearance of time dilation and length contraction. On top of this, Bohmian mechanics has to mysteriously exempt the pilot wave from the clock interference issue, since they would have to account for faster than light signaling. Assumptions on assumptions keep adding up in order to explain something standard quantum field theory can do quite easily. In other words, the data that infers things like time dilation, length contraction, and relativity are not really true of reality, but only appear to be so according to Bohmian mechanics. But there is no extra evidence to infer that what our data tells us is just a trick of the universe. All evidence should simply mean that there is no such thing as absolute time, and time dilation and length contraction are real features of the universe. So in times like this, we invoke Occam's razor to remind us entities should not be multiplied beyond necessity. If the evidence infers relativity is true, there is no reason to add an extra unnecessary assumption that the theory of relativity is just a trick and absolute time does in fact exist. Bohmian mechanics does nothing more than overcomplicate reality with extra unnecessary assumptions that are not needed in order to account for all the data. Sure, it is possible proponents of Bohmian mechanics are correct, and their overcomplicated theory is true, but there is no extra evidence that lends any weight to it, other than philosophical assumptions about how we think reality ought to act. Therefore, it should be shaved off in light of a simpler theory that can account for all the data. Connected to this is the fact that Bohm's quantum potential has been experimentally falsified by the Michelson-Morley entanglement experiments, as physicist Antoine Suarez points out. This was an experiment in an attempt to find the ether, a substance believed to fill empty space, and of course they did not. However, Suarez has explained it falsified the existence of a measurable quantum potential. It does not seem required if one considers that the falsification of the prediction 7 results by induction from the Michelson-Morley experiments repeatedly performed in the past. To this extent, the negative result of these experiments can be straightforwardly extended to the entanglement version presented in the precedence section to conclude that shift predictions by 7 will not be observed. And this means that the Michelson-Morley entanglement experiments rules out Bohm's infinite speed time-ordered quantum potential. Now, there are versions of Bohmian mechanics that exist without a quantum potential, or have a different type of quantum potential, but they are far more ad hoc since they lack a theory that can be falsified. So in order to deal with the conclusions, the remaining theories of Bohmian mechanics have to become more ad hoc, taking it out of the realm of testable predictions. This doesn't mean Bohmian mechanics has been completely falsified, just that any testable theory of Bohmian mechanics cannot exist. And there are even more issues with Bohmian mechanics besides this. Another issue is how Bohmian mechanics would produce the randomness we see in quantum mechanics from deterministic laws. In quantum mechanics, we accept that we get randomness. We measure to find out where a particle is, and the position is randomly selected. But Bohmian mechanics says this is not real randomness. It is randomness from ignorance. In reality, there is a deterministic wave guiding the particle to its position, and since we lack the ability to know the initial position, it only appears random to us. The problem here is this also violates Occam's razor by adding unnecessary extra laws that standard quantum mechanics can explain in much simpler terms, namely that there is randomness, fundamental to reality. Bohmian mechanics, in trying to save realism in a deterministic universe, has to posit an extra unfalsifiable force, which standard quantum mechanics can explain without positing, and simply accepts there is randomness that is fundamentally part of the universe. Much of the reason for this seems to be that proponents already presuppose the universe is deterministic, so the universe can't possibly be probabilistic. So there must be underlying deterministic laws we can't detect, which is a casebook example of violating Occam's razor in order to save preconceived notions you may have about reality. The next issue is Bohmian mechanics has to include the landscape of a many-worlds interpretation, which is why some have called it a many-worlds interpretation in disguise. Let's remember the wave function is not set to one possibility until collapse under quantum mechanics. Many possibilities exist in a superposition. The same is true in Bohmian mechanics, even though it is a guiding wave. In Bohmian mechanics, based on the initial position, the guiding wave, the Bohmian hidden variable, will guide each particle to its final position. But the evolution of the wave function, Bohmian or quantum, still includes many possibilities. Under Bohmian mechanics, they are simply referred to as empty wave packets, since the pilot wave did not guide the particle on the other possible paths. So if under Bohmian mechanics, the wave function is physically real, and there is no collapse of the wave function, as J.T. Cushing stated, then all the possibilities of the wave function are equally real in some sense, which is why you end up with a many-world structure. The guiding wave doesn't collapse to only one position, because there is no wave function collapse. So all the possibilities must equally happen in the mathematical formalism, as Harvey Brown and David Wallace stated. In the general case, each of the non-overlapping packets in the final joint system configuration space wave function has the same credentials for representing a definite measurement outcome as the single packet does in the predictable case. The problem, if it is one, is that there is more than one of them. But the fact that only one of them carries the de Broglie-Bohm corpuscles does nothing to remove these credentials from the others. Adding the corpuscles to the picture does not interfere destructively with the empty packets. Since Bohmian mechanics rejects the collapse of the wave function, proponents cannot infer the empty wave packets, as they call them, are less real, so to speak. the mathematics of the Schrödinger equation points out the superposition is a fact, and that it cannot be overlooked or simply dismissed. And they all must equally happen in Bohmian mechanics. H.D. Zay says, "It is usually overlooked that Bohm's theory contains the same many worlds of dynamically separate branches as the Everett interpretation, now regarded as empty wave components, since it is based on precisely the same absolutely real global wave function. And if Bohmian mechanics has to include a many worlds framework, the issues we went over in our critique of the many worlds interpretation apply as well to Bohmian mechanics, so it faces several other issues with its coherency. Furthermore, it really shows Bohmian mechanics is extremely ad hoc and violates Occam's razor here as well. If you have to adopt the many worlds framework, why even posit Bohmian mechanics, as Brown and Wallace point out? The mathematical formalism of the Bohm theory, after all, consists of two elements: the quantum state vector or wave function, evolving according to the Schrödinger equation, and the corpuscles, represented by a Poynting configuration space. The Everett interpretation requires only the first of these two elements. So why is it not Bohm's theory, rather than Everett's, which contains excess ontology? Which brings us to the most important objection, and the one we've been referring to the entire video. Bohmian mechanics is ad hoc and violates Occam's razor in general. We should note that proponents of Bohmian mechanics have offered responses to some of these issues, and many have called their solutions quite elegant. But it doesn't matter if we think they are pretty or elegant. They have to invent an excessive amount of new physics and mathematics that standard quantum mechanics can explain quite easily, and some still contend on whether their solutions work or not. So in order to save their theory and rescue realism from the measurement problem in standard quantum theory, they have to put out a theory that is quite ad hoc and convoluted, with excessive baggage that the standard theory doesn't need.
Well, David Wallace, philosopher of physics, put it in a way that I find very compelling. He says, faced with the measurement problem that we're looking at here, the philosophers instantly want to add new physics. The physicists are like, we just need better philosophy, right? And so as a physicist, there's a whole nother equation, a whole nother thing. And as we'll get to, I believe in a much sparser, leaner, and meaner version of quantum mechanics. So I just think that none of this is necessary. And when you get to things beyond a single particle or a single dart, when you get to the wave function of the universe and quantum fields, it becomes much harder for this formulation to even be written down.
The main reason many look for a different interpretation beyond the standard is, quite frankly, the philosophical implications it brings, as Maximilian Schlauhauser says. In the standard and Copenhagen interpretations, it is essentially the user who simply chooses the particular observable to be measured and thus determines which properties the system possesses. This positivist point of view has of course led to a lot of controversy, since it runs counter to the attempt to establish an observer-independent reality that has been the central pursuit of natural science since its beginning. The Copenhagen interpretation is a pragmatic and positivist interpretation, but once you include the philosophical implications of it, you lack an observer-independent reality, which many philosophically do not want to accept for whatever reasons they may have. So despite that the most parsimonious interpretation of the data leads us to a standard or orthodox interpretation, many do not want to accept the philosophical implications of this and seek a more convoluted interpretation, which is why we get interpretations like Bohmian mechanics, an attempt to save realism from the observer effect. But it simply posits too much extra physics, which is not verifiable or falsifiable. Proponents of Bohmian mechanics often state that their interpretation makes the same predictions as standard quantum mechanics. Well, yes, that is true, but it is also the problem. It makes the same predictions by positing so much extra in order to explain what quantum mechanics can without the excessive baggage. Bohmian mechanics makes all the same predictions, but has to drastically violate Occam's razor in order to do so. David Bohm even implied his theory was only an incomplete possibility and did not have the same predictive power as standard quantum theory. The only purpose of this phase of the work was to show that an alternative to the Copenhagen interpretation is at least logically possible. But the truth is, no one denies that Bohmian mechanics is at least logically possible. But possibility is not probability, and certainly doesn't mean it will get past Occam's razor. The truth is, just about anything is possible. I could create an interpretation that all the quantum states we have ever observed were divinely planted to trick us. That is possible, but it is not probable, and posits excessive events that are not necessary in order to explain the data. So just telling us Bohmian mechanics exists and is possible doesn't show it is the best explanation of the data. And if the only reason it is posited is in order to avoid the philosophical implications of the orthodox or standard interpretation of quantum mechanics, then there really are only emotional reasons to hold to it, not logical or rational reasons.